So now we are going to do the exercise problems from chapter 2 on Libre text, book by Tro. So this is chapter 2, taking measurements. Here, so these example questions, as I said, are your homework questions, but the exercise problems are mine. So and here example. And again, some of the exercise problems are not shown or given. So let's do these. Example 1 is done, exercise. So here, this one I'll do. So this is already done and explained. Okay, now let's look at this. What would be the reported width of the rectangle? So here's this rectangle given. And this question basically relates to, well, one is the uncertainty, one is the precision, taking, and then the accuracy. So all these concepts. Now, accuracy is when the results match with the true value. Okay, so that's one thing when it's accuracy. Precision is when you keep repeating the steps. In other words, you do a few trials and your results are same in all the 3 trials. So if they are the same in all the 3 trials, then you have to see if they match with the true value. If they match with the true value, that means your experiment, your measurement is precise and accurate. Next is you can take, your results can be, you repeat the trials, but every time you do, some new result comes, new method, new date, new result is there. So, and then your exercise, it's not matching with the true value. So in that case, that means you've made a mistake. Okay, and that mistake could be due to the way you take the measurements, or it could be somewhere in the calculations. Next is if you get the results which are, the date which are precise, and then the accurate, precise and accurate, this is ideally what you want. But if you have precise results but not accurate, that means there is some mistake. Now, mistake can also come sometimes when the students are taking measurements and they're not sure where they should look. So I wish I can expand this, but here you see that in this case, if you look at these, so this is 0.5, this is 1.0, this is 1.5. Now, right in between these 2 lines, there is nothing here. It's all like blank. So there are no lines here. So here you will have to use some estimation. You have to use just some estimation. It could be, so this is 1.0, this is 1.1, 1.2, 1.3, 1.4, 1.5. So between 1.2 and 1.3, there is some ambiguity. So it depends who is taking the measurements and how much ambiguous can you, like how much of the uncertainty or ambiguity can you tolerate. So some students will write down 1.2, some will write 1.3, some can write down 1.25 or 1.26. or 1.24. You see that? So this ambiguity comes because of this thing. So this is the reason why we have all these significant figures, rules for rounding up, and how far can we go after the decimal places. We can tolerate the uncertainty. So in this case, we for sure know that it is 1.2. That's for sure. But after that, we are uncertain. So the uncertainty is 0.0, like plus minus 0.01. So it can be 0.25, it could be 0.24, it could be 0.26. So that's uncertainty. But anyway, what would be the reported width of this rectangle? So when you look at the angle, like, it can be anything in these, the answer could be any one of this. So you like the based on what I told you. Okay. Now, the significant figures, there are rules regarding the significant figures and their exact numbers. So we talked about the rules in the previous videos, but let's quickly do a review here that non-zero numbers are always important, significant. So 237 is 3 significant figure, 1.897, 4 significant figures. If there are zeros that appear between the non-zero numbers, those are also important. Important means you have to count them in calculations and in, whenever you're computing them. So 39,004. So all these zeros, so that makes these zeros are adding value to this digit. So this is 1, 2, 3, 4, 5. Okay, this one is 5.02. So this embedded zero, the middle zero, this is also counted. So there are 3 significant figures. That means important. Next is the zeros that appear in front. Now those are called the leading zeros. Those are not important. So those are not counted. So those are ignored. So it's only the first number is 8. So 8 is, this is only one significant figure. Now here 0.000, these 4 zeros are all dropped. So only 3 significant figures here. So anytime you have these type of numbers, the zeros, the leading zeros are all dropped. Next is the zeros that appear after. Now here, this is an exact number. This is an exact number. Exact numbers are what numbers? Which do not have a decimal. Those are exact numbers, okay? So in this exact number, 1400 will have several different like it will have variable significant figures. So what does this mean? Because this number can also be written in scientific notation. All exact numbers can be written in scientific notation. You don't see the decimal, but the decimal is embedded. The decimal is right there. So you take the decimal and then you can like just move the decimal. So if you move the decimal, like from here, 1, 2, and 3 places you're going to move. So it becomes 10 to the power 3. But then who is doing the who needs this data? For what purpose? How far you can have the uncertainty? So after the decimal. So it depends on the person or the context in which the measurement is being taken. So ideally, this is a scientific notation 1.4. In other words, the dot, the point between the 2 digits. That is the scientific notation, times 10 to the power 3. Here 1.40. So that means 1.4 has to be like there, but you can tolerate some uncertainty in the second place, right? Here, this 0. And then same is the case here. So the further away the numbers are after the decimal, I mean, all the other numbers after the decimal are important except the last number. The last number can fluctuate. So here, so these are 4 digits, 4 significant figures, 3 significant figures, 2 significant figures, obviously, okay? And so that is why it is uncertain for all exact numbers, okay? But the ones that are trailing zeros, now these trailing zeros, what does this mean? Trailing zeros with the decimal, they're always counted, always. So this means that when you're taking a measurement, your measurement should be exactly at 620.0. So you see that anytime we have these decimals, we are using some kind of a measuring device. And anytime you use a measuring device, you will always have this type of a problem where there's going to be some empty space and you will have to use some measurement, some kind of estimation. So that's where the ambiguity comes in. So the last number fluctuates, so that's okay. So here 19.000, these are 1, 2, 3, 4, 5 significant figures, okay? Now give the number of significant figures, all this. Now let's do these exercises. All right, here, look at this exercise. Give the number of significant figures in each. So because there's a decimal, so all the 3, so there are 3 significant figures. Now in this case, the second one, 0.006606. So here the leading zeros, all these zeros in front are dropped, but the imperative or the captive 0 is counted. So 1, 2, 3, 4 significant figures. Okay. Next is 2002. So all these zeros are captive figures, captive zeros, they are counted. So this becomes 4 significant figures. Here we have an exact number. So here it is variable. For every time the exact numbers, exact numbers, yeah, for the people, obviously it can't be anything in decimal. It's the new counting number. Exact numbers are counting numbers. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 significant figures is the max. So it can be anywhere from like 2, because you can write numbers in scientific notation, right? To condense the number. You can write them in scientific notation, but you can also write them in exact numbers. And with that said, we can also have ambiguous, like variable. So from anywhere from 2 to 9 is going to be the range. You can have infinite or, ambiguous or, okay. Then 3800. This is also an exact number, and this is grams. So 3800 grams, exact number. And in this number, this is again a counting number. Let's say you had candies and you put all the candies on a machine and you get 3800 grams. So that's the weight of those candies. So this is again, can be written in scientific notation. Okay, so for all exact numbers, it is infinite or ambiguous. Okay, it could be 2, it could be 3, it could be 4 significant figures. Okay, so for all exact numbers, it's like that. So we talked about accuracy and precision. So here, if you look at this here, the center is the true value. If you look at in this problem, the center is the true value. So if you have the data points that are not matching with the true value, but they are still together in the same range, so this means that the first one is a precise. This is reflecting precision. This one is reflecting there are few data points that matched with the true values, but some of them were precise, means you repeated the experiment and they gave you the same results, but they did not match with the true value. So this could be like some are accurate and some are precise. Okay, so in this case, so in the set B is the set is it can be, you know, precision also is there, but accuracy is also there. In this case, so all the data are accurate. So last one. So the D is the C is basically so C is a set of measurement that is neither precise nor accurate, which target shows neither precise. So here you see all of them are accurate and precise also. So they are all like bunched up together. Here, this is neither accurate nor precise, because one trial gave you, so these rings are representing the trials. So one trial gave you one result, another one gave you another results, another one. So too many mistakes in every trial, and none of them are matching with the true value. So this is set C, neither accurate nor precise. Okay. Now, next is the rounding numbers. So when we round numbers, so if you are, you know, depending upon this, so here's the thing, do not round down, keep the numbers as is in chemistry. Next thing is that when you're rounding numbers, you have to match your results with the significant figures. What significant, so never round up or round down during these steps, but always round up or you know, whenever the final answer is. So what is the deal with that? Rounding is only cosmetically, you know, cleaning up the numbers, making them look clean, nice. That's it. So they don't, like, that's the only value they have. So let's do these problems. I'm going to just pause the recording for a minute. All right, so I'm sorry, we're going to record this now. So measurements, chapter exercise problems 2.4.2. Okay, so this relates to the significant figures in scientific notation. Writing the numbers on the significant figures, doing the calculations using the significant figures and writing the answers in scientific notation. So first of all, these are these rules. The rules are that when, the rule is that when we divide and we multiply, the final answer in the case of division and multiplication is going to be in the lowest significant figure. So you look at the computation, whichever has the lowest significant figure, that then you are going to do a final answer. If the division and multiplication is carried out, it will have that. If the addition and subtraction is done, then we are going to look at the decimal places. And in addition and subtraction, we look at the lowest decimal place, okay, in the final answer. So that's one rule. Second rule is the rule regarding the rounding up and round down. So for the chemistry matter, we do not round down, we only round up, okay? And rounding up is always done in the last stage, in the final stage, final answer only. So this is done in final answer only, not in between the steps. Final answer only. Let me put this here, note. I'm going to upload all these notes, so you will have this final answers only. Okay, so do not round up in between the steps. Okay, so leave them as it is. So in case of doubt, always use significant figure rules. And also you can just leave the numbers raw in the steps. Okay, so when we are rounding up or down, so what we do is we look at the dropped number. If the dropped number is 5, and the number on the left hand side then becomes, if the dropped number is 5, then the number that is on the left hand side will be, you add 1 to it. The dropped number is 5, you add 1 to the left side number. But if the dropped number is less than 5, then you leave the left side number as it is. So this is a simple rules regarding the rounding up and rounding down. Next is, so we looked at this problem where 207 was divided by 903. So what do you do here? In this case, both of them are the exact numbers. So there is a chance that there is a variation. So this exact numbers can have variable significant figures, but still there's maximum and minimum. The minimum can be 1, maximum is 3. So 1, 2, 3, all these significant figures are possible for exact numbers. Now, division, you divide from the calculator, just write down, so this number is as is seen on the calculator. So we need to keep the maximum number of significant figures. In the exact numbers, it's always you always keep the maximum, the one that is the maximum. Okay, so the maximum is 3. So you're going to keep 3, you're going to drop off the remaining. So you're going to here drop off number 3. So 3 is less than 5. So what is going to happen to 0? 0 is going to remain as it is. So now your answer is 0.240. 0.240. Now 0.240 here in the standard form is fine. If the multiple choice is showing you this number, you just choose this. But if the multiple choice is specifically showing you scientific notations, in that case, you will have to move the decimal. So you take the decimal, always move it in between the first 2 digits. And because you moved it only one place after the decimal, or one place was moved, one place, then that is how it is -1. So one place to the right is going to give you a negative exponent. This matches. Okay, so this is one thing. Next is you have these numbers where you are basically adding. So in this case you add, but in adding, so the way I remember is, you don't forget it, the D sound. So D sound matches with the decimal sound, D sound. So that's how. So you're going to look at the decimal places here. So decimal places, 2 places in the first one, 3 places in the second one, and the last one ambiguous. So leave it. So your final answer should only have 2 decimal places. Okay, so when you add, you see this number from the calculator. This is the number that is seen on the calculator, 1436.996. So you are going to keep only 2 places after the decimal. Now here's the tricky part. You see that 6 is more than 5, right? 6 is more than 5. So what is happening here? We will have to round up. So 9, when it becomes +1, it becomes 10. So you will keep 0 in the place of 9, but the 10, one of the 10 gets carried over to the next number. The next number is 9. So you add 1 more to it, it becomes 10, right? So you're going to retain the 0, 0, 0, but that 1 gets now carried over to the next number, which is 6. So 6 now becomes 7. So that's how the rounded off number is now 1437.00. Now this is a standard notation. Those 0.00, they have a value. They have a value. If you're going to take a weight, so this means it should not be 0.1. It should not be 0.01. Like the number should read as 0.00. Remember, we're talking about matter in chemistry. Matter is very I mean, you cannot reduce the matter unless you throw away the matter. So anyways, now here you have this 1437.00 in the standard notation is fine. But if you're writing it in scientific notation, you're going to move the decimal. Now you move the decimal 3 places to the left. 3 places to the left. 3 places to the left. And when you move 3 places to the left, that 3 places to the left shows here 10 to the power +3. Okay, you move to the right, it's negative, but you move to the left, it's positive. Okay, so here we see this number now becomes 1.437. Now, ideally, those 3 digits, those zeros, it depends how sensitive you want after the decimal place, how the data to be. But generally, as a rule, 2 places or 3 places after the decimal are more common. you know, because our equipments generally can only handle that much of sensitivity. In order to have certain numbers after the decimal, then you need to have very sensitive equipments also. So this is a common answer. This is correct. Okay. Now we are going to look at the next one, 255.0 minus 99. So what we are doing here is we are basically going to look at, so this is subtraction. So we're looking at the decimal place. So it's still, even though it is 0, it has a value. It means it is 1 decimal place. 99, no decimal. So, I mean, it's an implied decimal, but still it's not considered. So your answer should be 1 decimal place. Okay, so now we do 255.0 plus 99. And what do you get here? You get 354. Now from the calculator, now this is from calculator. Okay, we have this exact number, but the answer should have 1 decimal place. So what are you going to do? You're going to then make it 354.0. Remember, there's always an implied decimal, but this is the right answer. Okay, now let's look at the next question. Did I make this? This was. Oh, I made a mistake actually. I think I divided it. 255.0 divided by 99 is, no, what did I do? I don't know how I got this 354. I punched the wrong number. I'm sorry. I don't know how I got 354. I don't know what I was thinking. But anyway, so ignore it. Or maybe, wait a minute. I don't know how I got, maybe I had the wrong number punched in. So anyways, so let's remove this. But just you get an idea in case you do hit in a snag like that, and that's how you fix it. But let's fix it now. So 255.0 minus 99. And yeah, 156. So you have 156 here. Okay, so this is 1 decimal place. So final answer should be, final answer should have 1 decimal place also. So what are we doing here now? So 255, this becomes 156. Okay, so the final answer should also have 1 decimal. So in this case, you can just put 0 from your side. Okay, just to catch up on that, 156. Okay, 0.0, because your answer should have a decimal place. But so this is the standard notation now. So standard notation answer is 156.0. But scientific is you're going to move the decimal place. So in this case, you moved 1 and 2, 2 decimal places. 2 places you moved the decimal. So what this become? Then this becomes 1.5. And then 6, and I'm going to just put it like that, into 10 to the power. How many places did you move? You moved 2. So it becomes 10 to the power 2. But your final answer should have only 1 decimal place, right? So again, here, the final answer becomes 1.5 into 10 to the power 2. You got it? Any questions? Okay, so ideally they should give the units also, but they haven't. But this is the answer. All right, now we have, now in the book, they have given you 2 decimal places. No, if the rule is 1 decimal place, then this should also be 1 decimal place. Okay, so this looks like a mistake in the book. The rule is 1 decimal place. But yeah, like I said, we prefer to have 2 decimal places. So it's kind of like, it's all, it's in what context are we using these numbers? All right, next look at this one, D. D is 0.00666. 0.00666, 6 and 6. Okay, times 321. Okay, so here you see you have multiplication. So this is, these are dropped, not counted. Okay, these are not counted, but these are three significant figures. Okay, this is variable. It can be 1, it can be 2, it can be 3. Okay, three significant figures. So this means that, do you guys understand the exact numbers, how they are variable? Because they can be written in scientific notation. So if this number is written in scientific notation, it's going to be like 3 into 10 to the power 2. So let me just do it in case you're not. So 321 can, so there's an implied decimal here, which you don't see. So you move 2 places here. So one way would be 3 into 10 to the power 2. The other one, more exact, is 3.2 into 10 to the power 2. And the other one is 3.21 into 10 to the power 2. So you see that this is so it can have 1, 2, and 3 decimal, three significant figures. That's how. Okay, so anyways, so now we have this scenario. So your answer, technically, when we are multiplying your answer, so exact numbers, even though they have all these variable significant figures, we ignore them. So your answer, final answer, should have how many significant figures? 3 significant figures. All right. So here we see that point. Now, when you're doing the calculation, you're going to write down the full number the way it is, which is 0.00666. Okay, times 321. And that is 2.13786. So this is the number I see on the calculator. Okay, now this number has to be made into 3 significant figures, which means we're going to have this number, and this number, but we're going to drop 7. 7 is more than 5. Therefore, 3 plus 1 becomes 4. So now your actual number is 3. So this becomes 2.14. Okay, and now comes the question that 2.14, that is the standard notation. But in scientific notation, how do you write this number? This already is like partially scientific. So what does this mean? In this case, this is 2.14 into 10 to the power 0, scientific notation. So just in scientific notation, just to fulfill that, thing, the scientific notation always will have like times 10 to the power something. So because we did not move the decimal, there was no need for the decimal to be moved, and the number itself is 2.14, or like in the category like 2, so it's 10 to the power 0. Okay, any questions? Any questions so far? Okay, now I have this question coming from I think it was Chevron, and this is a question you asked me. This is the 2.4.3. Okay, complete the calculations and report your answers using the correct number of significant figures. So answer in the correct number of significant figures. So here we will be using PEMDAS. Okay, so PEMDAS, you understand? Please excuse my dear Aunt Sally. This means M is the multiplication, D is the division, A is the addition, and S is the subtraction. And this is the exponent and the parenthesis. So this is the brackets, and this is the exponent. Exponent is 10 raised to the power whatever. So this is the order of operation. Okay, so let's look at this answer here. This question. So A, 5 brackets 1.008 seconds minus 10.66 seconds. All right. So the units are given, which is a good thing. Okay, so what do we do here in this case? We are going to now first solve this part, parenthesis. So this is multiplication. So this means 5 multiplied by 1.008. Okay, multiplication first, and then subtraction comes in the end. Now, when you are multiplying, you look for the lowest significant figures. Okay, but we cannot make it 1 because 5 is 1. So we have to ignore the exact numbers. Ignore exact numbers in significant figures calculations. Okay, in fig calculations. Okay, so we will ignore. So lowest significant figure, technically here we should still have the 4 significant figures here. Okay, in this case also there are 4 significant figures, but because it is subtracting, remember, we are going to look at the decimal places, so 2 decimal places. So whenever you are doing subtractions, you're going to use the decimal places. All right, now we are doing this 5 multiply by 1.008, and here you have 5.04. So this becomes 5.04. Now, from my calculator, it is showing that, but the lowest significant figure would be, well, that's an interesting one. Generally, we ignore it, but remember, 2 places, so this is 3. Okay, 4, even if you do 4, 1, 2, 3, 4, and then you bring zeros, so 4, yeah, put 0 here, 4 significant figures, that makes it. Okay, now, so that's one thing, and then subtract it with 10.66. So 5.040 minus 10.66, and you get negative minus 5.62. Now, keep this in mind that lowest decimal place, this is the lowest decimal place. This one got 3, so this one was 2. This is 2, this is 3 decimal places. Okay, so the answer should have the lowest. So you are going to keep these 2 numbers. So 5.62, that is the answer, negative. And that's put the units. The units are seconds. All right, that's the answer. Okay, so order of operation. Next is, so Chevron, you were asking this on the board. You understood this? You can type the answer. Okay, good. Okay, next is, we're going to look at the next problem, which is 99.0. So same story, 99.0 centimeters. Okay, plus 2 times 5.56 centimeters. All right, so here you see that you're going to do the multiplication first. So multiply this first. This is a total of 3 significant figures and 2 decimal places. So put a note of this. This is 3 significant figures and 1 decimal place. Okay, so let's look at this now. So 2 multiply by, so first solve this, 5.56, and you get 11.12. So here it's positive 11.12, and then the other is 99.0. Now remember that when you're adding, you only look at 1 decimal place. So this is like, you look at the lowest decimal place for the final answer. So this is now 2 decimal places. So your final answer should only have 1 decimal place, the lowest number. Excuse me. Final answer should have only 1 decimal place. Okay, so let's do this. 11.12 plus 99.0, and the answer is 110. From the calculator, 110.12. Okay, 110.12, but we only need to have one decimal place. So Sigfrid rules require that only one decimal place needed. So what are you going to do here? You are going to then drop 2. 2 is less than 5. Therefore, 1 remains as is. So therefore, the answer is 0.1. Okay, and this was, sorry, this was centimeters. This is centimeters. This is centimeter. And this is centimeter. Okay. Clear? So that's, now your book is showing, unless I made a mistake somewhere, 1 second, 2 multiplied by 5.56, and that gives you 11.12. 11.12 add 99.0, and that is 110.12. And so your book is giving you 2. They rounded it up for some reason. They rounded it up. See, rounding up is only making the numbers look cosmetically beautiful. That's it. Just a cosmetic fixture. All right, guys. Any questions so far? Okay. Next, we are looking at the problems that relate to the these units and the units and the interconversion of the units. Okay, so let's look at the, I'm going to stop just a minute, give me 1 second. Okay, so now we are going to just do the review on the units, and then we will do the problems, the exercise problems, using the units and dimensional analysis and, conversion factors sort of thing. So here's the thing regarding the units. So we use prefixes. What do the prefixes do? They define the measurement, whether it is a small measurement, whether it's a long or a big measurement, the magnitude of the measurement. So if you look at the measurements that relate to that, say, giga, mega, kilo, hecto, deca, these are very big measurements, large amount of substances. So what is the magnitude of that? So if you look at the deca is 10 times more, hecto is 100 times more, kilo is 1,000 times more, mega is 10 to the power 6 times more, giga is 10 to the power 9 times more. So if we are looking at, for example, in what context are you doing the measurement? If you're looking at meters, then it becomes like kilometer, decameter or hectometer, like that. But if you're looking at like liters, then again, kiloliters or mega, or kilo, like grams, you can also use it in grams. So grams is like a base unit, and then the kilograms is like 1,000 times more. So that's what, that's how we do it. But so the base units generally, like, it's considered to be just 1. So if the base unit is 1, everything is relative in science. So 1, and then how much more. The next is the small units. Small units are for magnitude, which are very, very small dimensions, small magnitude. So like decimeter, like deci, centi, milli, micro, nano, and pico. So deci is 1/10 of that unit. Centi is 1/100th of that unit. Milli is 1,000th of that unit. So that th sound, that shows that it is a fraction. Micro is 1, like 10 to the power -6 times, like, like 10 to the power -6 is like really small. 10 to the power -9 is even smaller, and 10 to the power -12 is the smallest here. Okay, so very tiny amounts. Like, for example, when they are looking at the concentration of radioactive particles in the air. So that's where all these pico and nano and, even the micro, like, amounts are used. For example, they're looking at a medicine, which is very, like, potent in the body, right? And a small amount of it can produce a desired therapeutic effect. So for that, we use like picomolar, nanomolar, micromolar, right? So small amounts, very, 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 very potent. Okay, so that's one thing. Next is the let's look at these in what context. So you guys already know that, yeah, so these are the quantities that we use. For lengths, we use meters, for lengths, we use meters, centimeters, right? Millimeters, kilometers, yards, feet, right? Those things. Next, mass is kilograms, grams, milligrams, micrograms, or tons, those things. Then comes the temperature, is Kelvin, then Fahrenheit, degree Celsius, okay? Then time is in seconds and hours, minutes, years, even half-life. Amount of substance, generally moles in chemistry, right? Then the electrical current, for example, ampere, and luminous intensity is candela. So these are all like the base units, but then all these units, you can recognize the unit. If the numbers by themselves don't mean anything, but if you recognize these units, then when you recognize the units, then you can see that in what context this measurement is taken. So here in this question, they're asking you, give the abbreviation for each unit and define the abbreviation in terms of the base unit. So kilometer, what is the unit, or how do you define, or how do you write the kilometers? So the kilometer is written as km. Milligrams are written as mg, right? Nanosecond is written as ns, small ns, right? And centiliter, centi is C and liter is L, so CL, right? So those things, okay? So that's one part. Let's look at the next. Okay, so now we are going to look at these units. So all over the world, these units were being used by, in different ways. So people who were like in one kingdom, they used, let us say, the king, the parts of the whatever the units, the measurement, the amount, the magnitude, the king defined. Then that unit was used in that. For example, let's say feet. So the king decided to use his feet or a certain, measurement from his side, and then everybody followed that as a reference. So everything else was either bigger than that or smaller than that, but there was always a reference point. Okay, then comes a situation when people started traveling. The trade increased between the kingdoms. Now there's a problem. In one kingdom there is a certain measurement, and in the next kingdom the measurement is totally different. So it became a problem even when the kingdoms were like usurped, or the newer kings came, and then there was a problem. So those things. So besides that, colonization, right? There are colonies all over the world. So they're these colonies, they wanted to have some kind of uniformity in measurement. So that's how we have this. The English units are more like standard, international standard units. So sorry, which ones are no, metric units are more like standard, international standard. So metric units are all over the world. We are using them as like uniform, like everyone. So grams all over the world. So grams and grams, using the grams, you can use the prefixes to define. So like kilograms or milligrams or micrograms, or, so those grams, so milli, micro, all those are used to define whether the amount, the quantity of the mass. Okay. Next is the milliliters. Liters, again, milliliters, microliters, deciliters, all those are used to define the volume of the substance. Then comes the kilograms, again, the big mass on a large scale. Then centimeters, the length. So centimeters, millimeters, right? Kilometers. So all these, again, define the length of a substance, of anything. So liters are the volume. So all these, in what context the measurements are done. So in the metric system, in the US, in the international system, basically everything is increasing or decreasing in 10 to the power whatever, whether it's a positive exponent or negative exponent. So that's one very simplified version. But the English system or the US system is different. We use still it's an older method. So 1 ounce, fluid ounce, pounds, inches, miles, quarters. So these are being used. Now, there's a problem. If you have a measurement in one that is international, and then there's one in the US system. So we need to have a method of equalizing the two. So here are some of these units that you see, which are, they have not given, but I've given you the tables, right? So in these tables, we look at some of these equalities are given between the English system and the metric system. And then we create these conversion factors. And in this conversion factor, we take whatever quantity that we want to convert from into the newer units. So that process is called the dimensional analysis, and I'm going to show you how that is done. Okay, so let's just look at this one simple one right here. We have let's say let's see this one. Yeah, 100 centimeter is equal to 1 meter. This is what is given to you. 100 centimeter is 1 meter. This equality is known. You can convert any unknown centimeter to meter, and you can convert any meter to unknown, to any unknown meter, any known meter to the centimeter. So you can interconvert using this equality. This equality has two conversion factors. One of them is 100 centimeter over 1 meter. And the next conversion factor is 100. The other one is the flipped one, 100. So you can flip it. You can take 1 meter and put it on the top, and you can take 1 centimeter, 100 centimeter, and put it on the bottom. And I'm going to show you how. So this way, these two conversion factors, then you can use them to find the unknown. So let's do these. So like here. So I'll show you how to do these anyways. So let's do the problems 2.6.1. So just give me 1 minute. Okay, so here you see, this is your handout. Now in the handout, I've given you these tables. Okay, these tables you can use as a reference for your homework, tests, quizzes, whatever, as you need them. It's very important in science. You should learn how to access information from the tables, okay, and read the tables. So anyway, so everything that you need is here regarding the prefixes. So prefixes are here, and then you have these other equalities where the metric system and the US system, these equalities are given, the conversions of this. So if you need to convert centimeter to inches, kilometers to miles, milliliters to quarts, all these are given to you. Then you're also given the US system, where how much feet is how many yards, and how many miles is how many feet, all those type of entities are also given. The other metric qualities are also given. 1 deciliter is 1 liter, 100 milliliters, and those are also given. Some of them are also given to you here. Okay, but you're welcome to add more from your side, because there are so many you can add from your side. But for general, so some are here and some more are here. So in what context? Like for all the length, the base unit, 100 centimeter is 1 meter, 1000 millimeters is 1 meter, kilometers is 1000 meter, all those base units. So these are all the relationship between the metric base units, and the relationship in the English units are also there. So kilometers and miles, and the relationship to the English unit. So these are also given. So you can use these tables. And then these are the rules regarding the significant figures, just so you don't forget them. So all these rules regarding the significant figures are here. And once again, here, a 0 is not significant figure if it is as a placeholder in a large number. So these exact numbers, as we talked about, so it can have. So here this table is showing that 2 and 3, that is incomplete information. This is variable. That is why I made this mark right here. This mark is signifying this. So for exact numbers, significant figures are variable. So in table 2.2 part 2b, this is what it is. So I have explained this, that this can have 6, 5, 4, 3, 2, 1 significant figures. Depends in what context you're using those numbers and the scientific notation. But anyways, so once again, moving the decimals from its original place, all this is also given. So you should you will be using your handout on the tests. So just so you know how to access information from the tables. All right. Now let's do this problem. All right. Okay, so we have the next problem is using the dimensional analysis, simple conversions. Okay, so this is exercise. This is problem 2.6.1. Okay, 2.6.1. And this is using the dimensional analysis, doing the conversions. So conversions between the units. Okay, conversions. So there is a term, so there's certain languages you also have to, understand that. To and from. So from is you are going to get rid of from. So converting from going to. So to stands for top. T for to, T for top. So remember that. Okay. So from is going to be in the bottom. And 2 is the top. Okay, so when you write them, these are basically fractions. So fractions, you will be given something, and this is some given units. Okay, so some given units are going to be here. You are going to multiply by that factor, that conversion factor, which is going to allow you to cancel the unit that matches with the given unit. Cancel this unit with, the given units. So these two should be the same, right? Same. So given units and this unit should match. They should be the same. And this unit is the one that you want. You want to convert to. So this is the wanted unit, goes on the top. So wanted goes on the top. And the one that you do not want, you want to cancel from. So this is the from part. And this is the to part. Okay. So now you see this unit, the given unit, and this unit will cancel out. And the unit that you want to stays on the top. So this part is called the conversion factor. Conversion factor. And this conversion factor is conversion factor. Okay, now how do you get these conversion factors? So let's just look at a few examples and then we will go from there. So here you see you are given, for example, let's say I'm going to do this one. Yeah, 100 centimeters. So 1 meter is equal to 100 centimeter. So this piece is known already. So known in the tables or either some of these equalities. So this equality is known. It is in the tables. Okay. So equality that is known is going to be your will form the conversion factor. So what are the two conversion factors? So this is going to be 1 meter over 100 centimeter or 100 centimeter over 1 meter. Okay. So these are the two conversion factors. And now you are, let's say, given 3.55 meters, right? And you have to convert it into, find how many centimeters is that? How many centimeters is this? So in other words, you want to convert meters to centimeters. So we want the centimeters. So when centimeters is wanted, so we are going to use this conversion factor where centimeter is on the top. You are given the meters, right? You're given the meters, but you want to cancel the meters out. So you're going to use the second conversion factor. So all you need to do is now put the 3.55 meters. Multiply that by 100 centimeters over 1 meter. Okay, so here you cancel out the meter and the meter cancels out, right? And you are left with 100 times 100, 3.55. Now 3.55 times 100 and you get 355. So the answer here is 355. Now the 355 alone doesn't make any sense. So what do we need here? We will need the units. So because that's why the whole purpose of doing the conversion was to you know, to get the new conversion, the new units. Okay. Now, next, so let's look at this problem from the book, which is 2 points. So this one, 2.6.1. So here we are given part A. So part A is 101, comma, 1000 ns nanoseconds. Okay. Convert that to how many seconds is that? Okay. How many seconds is that? So we see here that 1 second is equal to nano. See, nano. So back to that table, the nano. Nano is this number n, and 10 to the power negative 9. Okay, 10 to the power negative 9 means that it is now, you're going to take the 1 second and you're going to multiply it by 10 to the power 9. So let's do this. Let's get this. Where is that? Okay, so we know that. So this is known that 1 second is equal to 1.0 into 10 to the power negative 9 nanoseconds. Okay, so the other one is 1, 0, 1, 0, 0, 0 nanoseconds times that unit, that thing that cancels out the, so 1.0 into 10 to the power negative 9 nanoseconds, and this one is seconds, and this is 1 second. So this is the conversions. So this conversion factor, the conversion factor is 1 second over 1.0 into 10 to the power negative 9 nanoseconds. Okay, now, so next is, you can just do the math here. So we get 1, 0. So there's another way you can do. If you're doing it manually, let's do it manually, just in case you don't know how to do it. So you manually, using the calculator, you can do it, or you can just do this. Here is a decimal. So 1, 2, 3, 4, 5. So 5 places. So 1, 2, 3, 4, and 5. So this becomes 1.0 and drop off the remaining into 10 to the power 5. Okay, times 1 over 1.0 into 10 to the power negative 9. Okay, so so this would be nanosecond and nanoseconds cancel out. Nanoseconds cancel out, and you get this. So just let me finish the calculation on this one. Hold on. Okay, so sorry, I had the wrong exponents here. So 1 second is 1.0 10 to the power positive nanoseconds. Okay, so that's the thing that I was confused about. So sorry about that. So anyway, so now we have this number, which is in the standard notation, right? Standard notation, and we need to convert it into scientific notation. So it becomes, when you move the decimal, it's 10 to the power positive 5, and you can drop off the remaining just for the ease of calculation. So the two conversion factors of 1 second is equal to 1.0 into 10 to the power positive 9. So these are the one conversion factor. Why do we want this? Because the answer is asking us to find in seconds, so second goes on the top. The nano is what we want to cancel out. We want to remove. So that's why that goes in the bottom. So next is, you just set up the problem. 1, this is the nanosecond, this is the nanosecond, and this is the second. Okay, so here the nanoseconds and nanosecond cancel out. And now when you're doing it on the calculator, you can do it, but if you want to do it manually, so this becomes 1.0 into 10 to the power plus 5. Okay, times 1.0 into 10 to the power negative 9. So negative 9 minus 5, positive 5 becomes negative 4. Negative 4. So that is your answer. That's the second. Okay, so that's one piece. Now let's look at the next one, which is converting kilograms to grams. So the part B is 32.08 kilograms, and you convert that to grams. So we know here you're going to look in the periodic into this table. Let's say if you don't remember, so kilograms and grams, the relationship between kilograms and grams is 1 kilogram is one gram is 1,000 kilograms. 1,000 kilograms. So so here is, you write this down, equality 1 kilogram is equal to 1,000 grams. And then the two conversion factors are 1 kilogram over 1,000 grams, or 1,000 grams over 1 kilogram. And we need the grams, so that's why we are going to use this conversion factor. Okay, now write down the given, which is 32.08 kilograms. Okay, 32.08 kilograms. And then what are you doing after that? You're going to multiply it by that conversion factor that has the kilograms in the denominator, so that that can be canceled out. And we want the grams, so they are going to be on the top. So 1,000 grams and 1 kilogram. So here, kilograms and kilograms cancel out. So you get next is 32.08 times 1,000, okay, divide by 1. And this becomes 32.080 grams. Okay, so that's the answer. So always write the units. All right. Next is another way. So that's obviously is the scientific notation, but the standard notation is you're going to take the units, the decimal, move it 1, 2, 3, 4. So you moved 4 places. So this becomes 3.2, 3.20, right? Into 10 to the power, you moved 4 places, so 4 grams. Okay, 3.20. And if you look at the significant figures, then this is the 4 significant figures, right? So your answer should also be 4 significant figures. So in order to do that, you're going to still have that 8. So 3208. Okay. So like I said, there are milligram balances also. So 3.208, you can measure that like, but it's 10 to the power 4. So it really is not really, I mean, it's just, it's making these numbers look nice. That's the only thing. So that's the answer. Okay, that's the scientific notation. All right, next is the answer to this one. 1.53 grams. So C is 1.53 grams is given to you, and you convert the grams to centigrams. Okay, now centi is relates to like centimeter, meter, so 100 times more. So that means 1 gram is 100 centigrams. No, one, or is it the opposite? I always get confused here. So centi is 10 to the power -2. So 1 gram would be 100 centigrams. Yes. 100 centigrams. Okay, so here you're going to write down again the 2 conversion factors, because we want the centigrams. So 100 centigrams on the top and 1 gram at the bottom. So this is the conversion factor that you are going to use. CF is the conversion factor. So 1.53 grams times 100 centigrams over 1 gram. So here 1.53. So in other words, this is 1.53. This means that the grams and the grams cancel out, and you have 1.53 into 10 to the power 2 grams. Okay, that's the answer. Centigrams, sorry. Centigrams, not grams, centigrams. All right. Okay, so this has taken one. Now, multiple conversions. Same is the case, multiple conversions. You take one, you convert it into another and another. So, you know, I'm thinking it's very time consuming to do every single problem, but I'm thinking I should just do one or two exercises from every, that might be better because it's very time consuming. So anyway, so here we have 2.7. Let me see how much more is left. 2.7, 2.8, and 2.9, 2, and okay. So we just have a little bit left, but for the future chapters, I'm going to do you know, only one or two questions from exercise problems, not every single one of them, because it's consuming a lot of time. So let's do this now, the multiple one, where it's going through the multi-step conversions. So here you are not given the direct conversion. So this is the indirect conversion. So this one now is 2.7, 2.7.1. Okay, so here perform each conversion in one multi-step calculation. So one multi-step calculation is all in one line. Okay, so here you are given, the first one is the nanograms to kilograms. So 43.007 nanograms. And you have to convert them to kilograms. How many kilograms is this? Convert it into how many kilograms? So there is no direct conversion between the nanograms and there's no direct conversion between the nanograms and kilograms, right? So you have to go by the indirect conversion, which means you take the nanograms, that is like 1 gram is equal to 10 to the power 9 nanograms, convert to that. Convert the nanograms to the grams, and then take the grams and convert the grams to kilograms. Okay, so here, these are known quantities, known that 1 gram is equal to 10 to the power, like 1.0 into 10 to the power, basically we write it like that, 1.0 into 10 to the power 9 nanograms. Next is 1 kilogram is equal to 1000 grams, or 10 to the power 3 grams. 1.0 into 10 to the power 3 grams. Okay, so this is known. Now what will you do here? You're going to take first, this is the map you will make. You're going to take the nanograms, convert to grams, and grams to kilograms. Okay, so 43.007 nanogram time. We need to cancel the nanograms, so that goes in the denominator. We want the grams remain on the top. So 1 gram is 1.0 into 10 to the power 9 nanograms. Okay, this step converts the gram to brings it to grams. Next is we need to convert to kilograms. So we know that 1 kilogram is the degree, that is the unit that we want, and 1.0 into 10 to the power 3 grams is what will allow the grams to cancel out. So this gram and this gram cancel out. This nanogram and this nanogram cancels out. So what is left now is that, so you can do it like this, 43.007 into 10 to the power -9 into 10 to the power -3. Okay, so negative, so this becomes 43. So this is the basically 43.007. I'm going to just leave it like that first, into 10 to the power. Remember, -9 and -3. So minus and minus in the multiplication. In multiplication, minus minus r become plus, but the sign will be added. So this becomes negative 12. Okay, but we need to write this number in a scientific notation. So this thing gets moved here, one place. So when it's in moved one place, this becomes 4.3007 into 10 to the power negative 11 kilograms. All right, so that's one thing. That's part A. Let's look at part B. Part B is 100 inches to feet. 1005 inches to feet. Now let's look at the table. Here in this, inches to feet. Okay, inches to feet. So inches to centimeter is there. And then feet. Okay, inches to feet. So that's a direct conversion. Inches to feet is the direct conversion. 12 inches is 1 feet. Yeah, so it looks like it's a direct conversion. Centimeter. Okay, I'm going to change this because this is a direct conversion. I'm going to convert it to yard. Let's do that. I'm going to change this question because this is a direct conversion. So let's do this to yard. Okay, so 1005 inches to how many yards is that? So inches to yard. Is there a direct conversion? So look on the table. If there is no direct conversion given, which we see it is not, inches and yards are not, right? This is a unit of length. So we don't see this anywhere here. So what will you do? Inches, you're going to convert inches to centimeters, or inches to, or inches to feet. Yeah, here, inches to feet, and then feet to yard, right? So we know 1 feet is 12 inches. Let's write this down. 1 feet is 12 inches. Okay, and the next is 1 feet is 12 inches, and the next one was what? 1 yard is 3 feet. 1 yard is 3 feet. So the two conversion factors are 1 feet over 12 inches or 12 inches over 1 feet. Okay, here you have 3 feet over 1 yard and 1 yard over 3 feet. Okay, so these are the two conversion factors. The one that we need, how are we going to? So we're going to set up. So we need the inch, we need to get rid of the inches and we need to convert it into yards. So 1005 inches multiply by that conversion factor that rules out or cancels out the inches and converts to feet. Now we don't want the feet, we want the yard. So we want to cancel out the feet. So cancel, the feet goes in the denominator and the yard remains on the top. Okay, so rest fill in the numbers. So here you have feet, sorry, what is that? 12 inches and 1 feet. And here you have 3 feet and 1 yard. So you are going to use this conversion factor, 3 feet, sorry, no. You're going to use 1 yard over 3 feet, this one, and you're going to use 1 feet over 12 inches. These two conversion factors that allow you to cancel out these, okay? So you see this now, the rest, so what did I put here? 1 yard. Okay, so 1005 times 1 times 1 divided by 12 times 3. So this is 36. So 1005 divide by 36, and that is 27.91 yard. Okay, 27.91 yard. So that's one thing. And I just want to check one thing. Yeah, so if this part, the first part basically is converting this part converts the inches to feet, and the answer to that one alone is 83.75 feet. So that's what, one step that the book has done. This is a direct conversion. But next step is where you take the next step is where you take the feet and you convert it into yard. Okay. So that gives you the final answer, 27.91. Okay, next is, let's do this one, the last one, the C, and C is 12 miles to kilometers. 12 miles to kilometers. Okay, so 12 miles to kilometers. Again, miles to kilometers. Miles to kilometers. So this is the direct conversion is already given. Okay, miles to kilometers is already given, but I want that you should do it in, let's do feet, miles to feet. Let's do that. So miles to feet. Okay. So let's see, because direct conversion exists and this problem should be multi-step calculation. So let's do this one. Sorry, let's do this. So we know that here using this table, you see that, where did it go? So miles to kilometers. So 1 kilometer is 0.621 miles. 1 kilometer is 0.621 miles. All right, 0.621 miles. And the other one is the feet. So miles to feet, wait a minute, 5280 feet. 5280. Uh, 1 mile. 1 mile. Okay, so I'm making a mistake here. So miles can actually be converted directly. Miles can be converted directly to kilometers, and miles can be converted to feet also. Yeah, be using these equalities. Okay, so that's, I'm looking for, let's convert that to inches, 12 inches. 1 feet is 12 inches. 1 feet is 12 inches. So let's do that in inches. So miles to inches, sorry, because a direct conversion exists for these two. Okay. So there's no direct conversion between miles to inches. Miles to inches. There's no direct conversion. Okay. So what will you do in this case? In this case, it's indirect. So I'm giving you this, the problem from my side, miles to inches. And no direct conversion exists. So what will you do here? You are going to set up the problem in a way that you take the miles, given miles, first convert them to feet, and then convert them to kilometers. No, sorry, feet to, no, first convert them to the feet, and then the feet to inches. All right, so 12 miles times. Okay, we need the inches, you put the inches on the top. Okay, miles, as we said, first you have to convert them to feet, so feet goes on the top. You need to get rid of the miles, so this mile goes at the bottom. So this is how you set up, and then this feet right here. So you set up the problem like this. Okay, I'm going to just leave it like this so you understand that, you know, how to do this. Set up the problems, and then you can just, you know, do this more and more complex ones also. So here now, just plug in the numbers. So 12 miles, and we know that 1 mile is 5280 feet, 5280 feet, and 1 feet is 12 inches. So the rest is just the conversion factors coming from equalities. So this is the set up the conversions like this. Okay, so now we have 12 times 5280 times 12, divide by 1, divide by 1. So this is 760,320. Okay, so these many inches. Okay, that's the standard notation, but that's an exact number also. So if you write it in scientific notation, then it is kind of like, so okay, so looks like 1247. So you guys left, I think. Okay, that's fine. All right, let's look at the next problem, and then we will close this. All right, next goes the next one is, sorry. Okay, so the next problem is 191 square miles. You need to convert them to how many square kilometers is that? So the question is asking you in kilometers square. Mile square needs to be converted to kilometer square, but how many it is that? So we look at the equality, and in the equality we see that mile and kilometers, the relationship between mile and kilometer. 1 kilometer is 0.621 miles. So write that down. One kilometer is equal to 0.621 miles. Okay, so this is known. So miles is MI. MI is equal to miles. So I'll just keep it at MI now. So 1 miles is 1 kilometer is 0.621 miles. Now we want it in kilometers square. So this would become 1 kilometer square is equal to, so this whole thing has to be squared. So this also means that this whole thing, if we're talking about square, that 1 kilometer is equal to 0.621 miles. This whole thing needs to be squared so that, you know, it's kilometer square and mile square. So I'm going to just remove this for now, and let's set this up like this. In this case, 191 miles square times. Now, since we want it in kilometer square, so we will have to do this. So 1 kilometer, this is what we need. And we have 0.621 miles. And you square the whole thing. Okay, miles, and you square. So when we do that, this means that now 191 mile square, that's meter square, this is mile square times 1 kilometer square over, so 0.621 times 0.621, and that gives you 0.385 miles square. Okay, so this piece, this and this needs to be done if you want this answer. Okay, so this is addressing these issues. Now remember, this is also miles square. This is already given to you. This 191 miles square was already given to you. Square miles means mile square. So now you cancel out these miles square, and mile square this way gets canceled out. So 191, divide that by 0.385, and you get 496. 496.10 kilometers square. Okay, and you can also write this as 497 kilometers square, depends how sensitive the information needs to be. Okay, let's look at the next one. Okay, so these are the last questions, the last section on density. So we are given the volume in liters, and we're given the mass in kilograms, and they're saying find the density in kilograms per liter. So the simple answer here is, what is the density in kilograms per liter? So here we see that the mass over volume, that is the formula. Mass over volume is equal to the density. So here the mass is 10.0 kilograms, and the density is 36.5. The volume is 36.5 liters. So 10.0 divide by 36.5 liters, and you get 0.273 kilograms per liter. That's the value. Okay, so that's one question, part A. The next question is, and you can round up the last digit. Okay, next is, if you have, next part is the last part, which is the part B. Part B. Okay, here we are given, if you have 2.130 milliliters. Okay, milliliter sample of acetic acid with a mass. The mass given is 0.002234. 0.002234 kilograms. Okay, and the question is asking, what is the density? Find the density in kilograms per liter. Okay, what is the density in kilograms per liter? So we see here that the kilograms, we are okay with the kilograms, but we need to change the milligrams to liters. Milligrams to liters. Okay, so how are we going to do that? So we know that 1 liter, this is the, from the units, you can look at a table. Once again, you will be always using the reference in case you don't, after some time, you kind of remember that. So 1 liter is 1000 milliliter. You can get that from the table. All right, here we go. So 1 liter is 1000 milliliters. So what will you do here now? Next is, you're going to convert, first of all, 2.130 milliliters to liters. So 2.130 milliliters times 1 liter over 1000 milliliters. So what does this become? 2.130, divide that by 1000, and you get 0.00213 liters. All right, so that's the number you're going to use for the volume. The rest is density, is mass is 0.002234 kilograms. Divide that by the volume, which is 0.00213 liters, and that is 0.002234. Divide that by 0.00213, and that is 1.04. And here, let's do the significant figures. 1, 2, 3, 4. 4 significant figures. 1, 2, 3. 3 significant figures. So the answer should be, so this is 4 significant figures. This is 3 significant figures. And so your answer should be 3 significant figures. We're going to keep these 1.04. So on the calculator, we see this is 1.48. Now 8 is more than 5. Therefore 4, you add 1, and that becomes 5. So your answer is 1.05 kilograms per liter. That's the answer. Okay. So that finishes this. If I have density can also be used as a conversion factor, but pretty much, you know, let me just do this also. So 2 point, you can still use the, I mean, density. Okay, what does this mean when we say density as a conversion factor? So density as conversion factor. Okay, so density as conversion factor. What is that? Here, if we are given a density, let's say 1.3 grams per liter, this means that 1.3 grams is present in 1 liter, or 1 liter contains 1.3 grams. All right, so these are the two conversion factors. So if you are given 100 grams of air, if you are given 100.0 grams of air, okay, what volume? So that's the volume. What volume of 100 grams of air is? So we need to find the volume. Okay, grams. So the mass is given 100.0 grams. So write that down times that conversion factor that, you know, that allows us to get rid of the grams and that allows us to give you the liters. So that volume. So here the grams and grams cancel out. So this becomes 100.0, divide that by 1.3 and you have 76.923, so forth. Now here you see the, so 1, 2, 3, 4, 4 significant figures. Here you have 1, 2 significant figures. So it would be nice if we could have, I mean, it depends what you're doing. So we need to keep only 2 significant figures and drop off the rest. Okay, so the answer should have only 2 significant figures. So here you are dropping off 9. 9 is dropped, 9 dropped, and 9 is more than 5. So 9 dropped, and 9 is more than 5. So therefore, 6, you add 1, and it becomes 7. So the answer now is 77 liters. That's the volume, and that's the answer. Okay, so this is the answer from the book also. All right, so this finishes this chapter, and now the last one, they have given you some numerical problems, problem solving strategies, those you can do for, I mean, you can do those for practice on your own. Okay, plenty of problems are given here. You can practice on your own. Next, we're going to move on with the next chapter. That is the 3rd chapter. All right. Okay, so this finishes this recording, and thank you for watching. Bye.